Hey everyone, welcome to lesson 4 of theme 3 at GCSE Geography. We're going to move on to looking at volcanic landscapes and their associated features today. So we've done constructive and destructive plate boundaries, so you have some background understanding of how volcanoes are created. But there's actually three main categories, three main types of volcanoes, and there's lots of other features, both small scale and large scale, that you find in volcanic landscapes as well as the volcanoes themselves. So if you'd like to pause the video here a moment, go ahead and write down today's title and we can get started. Okay, so we're going to first cover the types of volcanoes: shield, strato and cinder, and then we're going to look at other associated formations like geysers and lava tubes and things like that. Now there's some key terms first off that you're going to need to write down in your book that we're going to be using today. Okay, tephra and ash, volcanic bombs, a pyroclastic flow, lava and viscosity. Okay, now when we think of a volcanic eruption, we tend to think of lava coming out, but there's lots of other things that come out There's lots of other things that come out of a volcano. Lava, yes, it's the molten, melted rock from underneath the Earth's crust, from within the mantle. This is called magma when it's still inside the Earth, and then it's known as lava once it has been extruded, once it has forced its way up through the crust and erupted out of the volcano. But you also get all these other things coming out during volcanic eruptions. You've got tephra and ash, volcanic bombs, which are large chunks of rock being spewed out of the volcano during the eruption, and a pyroclastic flow. This is actually the most dangerous volcanic product. Lava usually, depending on its viscosity, depending on how runny it is, therefore how fast it travels, you can normally actually outwalk some lava even, certainly outrun, outcycle or outdrive it. You can get out the way of lava relatively easily. Pyroclastic flows, on the other hand, this is what covered Pompeii in Italy. In 64 AD, I think. It's boiling hot ash and gas that races down at hundreds of miles an hour up to 1,000 degrees centigrade. That will literally engulf everything in its path and kill it. So pause the video here a moment and write down these key terms with their meanings, please. Okay, so the next thing, there are different types of volcanoes, okay? So what I'd like you to do is, accompanying this lesson, you have got this table. Now, if you don't want to use the printout of this that comes with the lesson, you can always put the subheading in your book and do it in bullet points or something underneath, or you can draw out this table in your book if you're not able to print it. If you're not able to print it, then I would suggest probably drawing out this table in your book on a sideways page and just leave these three top ones blank, and I can give you these pictures when you come back. What I'd like you to do is we're going to compare and contrast the three main types of volcano: shield, stratovolcano and cinder cone. Now shield and stratovolcanoes tend to be much bigger. They are large-scale features of a volcanic landscape, whereas cinder cone or scoria volcanoes tend to be much smaller. They are a small-scale feature of a volcanic landscape. What I'd like you to compare for each one is the size. So try and find an average height or an average diameter for each one. I'd like you to write in bullet point form is fine, some of the eruption products. What does an eruption of that type of volcano produce? Is it mostly ash, lava, pyroclastic flow, all of the above? Habit. This means how often does it go off? Okay, you'll find that some of these bubble away fairly frequently. Their eruptions tend to be smaller and more often, whereas others are less often and much larger eruptions. So all I want in there really is just a little description. Can't talk today. A little description. Something like, doesn't erupt very often. When it does, it's very powerful. Or erupts all the time, therefore eruptions are less powerful. Okay, and then location. So type into Google example of shield volcano, example of cinder cone volcano, and see if you can tell me an exact example and its location of a named volcano of that type in the world. Here are a couple of websites that you can use to help you fill in that table. You probably find information all over the place on the internet, but here are two of the websites that I found most useful to get you started. So job 1, print or draw out this table. Job 2, use these websites and anything else you can find on the internet to fill in that table, please. Pause the video here a moment and do that. Okay, so obviously in volcanic landscapes you're going to get volcanoes. you're also going to get other features. We're going to stick with large scale for now, and we're going to look at calderas first. Now, a caldera, very simply put, is a massive hole in the ground created in the aftermath of a volcanic eruption. So if I exit the show a second and go onto the internet here, all right, this explains a little bit about how calderas are formed.
A magma chamber extrudes lava onto the surface. As magma migrates up into the magma chamber from great depths, it encounters less pressure near the surface. As a result of the decreased pressure, the gases in the magma expand rapidly, creating massive volcanic explosions. After an eruption, the emptied magma chamber of a volcano can collapse, forming a large circular depression called a caldera. Calderas can be many kilometers in diameter. They usually have flat bases and steep slopes. Through time, the caldera basin may fill with water, forming a caldera lake.
Okay, I want you to keep in mind for a minute what you can see here. So quite often with calderas, they will fill up with water and you get a caldera lake. But in areas where the magma is still quite close to the surface, the heat from that magma often superheats this lake, creating a really hot caldera lake, such as the ones in Yellowstone. And I'm going to come to that in a moment. But if I just come out of this and back into this, you have got, with your handout, this little three-stage diagram. And you have also got some key terms here. You can re-watch that video using the link from the PowerPoint. Use these key terms to annotate these three diagrams. Oh, excuse me, first day back after Christmas. To annotate these three diagrams to explain what's happening. So I would suggest that you cut and stick this with room to write around it. Okay, so in the first stage, the volcano is erupting with lots of heat and pressure. In the second stage, the eruption has finished and the magma is draining down. The remaining magma has drained down into the bottom of the magma chamber, leaving an empty magma chamber. What will then happen is, because that magma chamber is empty, there's nothing holding it up, and because the eruption has finished, all of this rock will cool and contract and collapse in on itself. And that collapse forms the caldera. So pause the video here a moment and either draw out or print out and stick down, but then annotate this three-step diagrammatic representation of how a caldera is formed. Okay, the next feature we're going to look at, let's talk a bit more about calderas actually. I forgot this was in here. So here's a cross-section representation of the Yellowstone caldera. Now what we think happened in Yellowstone was there was a mega eruption several thousand years ago, in fact, a really long time ago. And it's left a massive crater called a caldera. And that caldera has filled with water, but the magma is still really close to the surface. This is still a really geothermally active area. Now, to give you an idea of scale, that line there, that's a road. And you can't quite make it out, but there's a couple of cars on there. Any suggestions or thoughts as to why this lake is rainbow coloured? This is not photoshopped. If you Google Yellowstone Caldera Lake, you will see this exact image. Why might it be multicoloured? What might be giving it that colour when there's intense geothermal heat from magma really close to the surface underneath this lake? What's actually happening here is this is bacteria. It's pretty much all that is able to live in this superheated water that has also got lots of acids and chemicals dissolved in it. So each of these layers represents a different type of bacteria, and it shows that there's like a temperature gradient of slightly different temperatures with different bacteria living in each level of temperature. And that's what creates the multicolours. There's different types of bacteria living in the lake. So the next landscape feature we're going to look at is much smaller scale, is lava tubes. Okay, it is a tube underground created as lava cools. It's literally what it says on the tin. All right, and here are some photos of some. You can walk in some of them. So although they are small scale features, they're still pretty big. To understand how lava tubes form, you need to think of lava like custard. Now, as custard cools down in a bowl or in a pan, what do you get on the top? It gets like a skin on it, doesn't it? The top and the outside of a flowing liquid will cool first, and it cools from the outside in. And that's how a lava tube is created. So a volcano might be erupting, and there'll be a flow of lava going on. But at the edges of that flow, and on the top of that flow, where the lava is touching cooler rock on the edges and the cold air on the top, the edges and the top will start to cool first. And as you cool flowing liquid rock, it starts to solidify, just like the skin on custard. And what that creates is like a roof, and sides begin to form, but the lava will still be flowing through the center as the eruption is continuing. Once the eruption finishes, all the lava flows through and out the other side, and you're left with this tube of cooled outer sides and roof. All right? So if we look here, here's your lava flow at the beginning of the eruption, and what it does is it begins to sort of melt and burn down through the rock that it's flowing over. Over time, the sides start to cool and build up layer by layer. And then it sort of meets over the top, creating a roof that also cools. But the eruption is still going on, so the hot lava is flowing through the center. Eventually, the erupting volcano will stop. All the lava will flow through and out the other side, leaving a cooled and solidified tube shape. Okay. Now you've got these 5 stages of lava tube formation diagram attached to this lesson. So you need to print them out and stick them down. And you've also got annotations to go one with each diagram. But these annotations are jumbled up. So what I'd like you to do is have a read of each of these and see if you can match them to the correct diagrammatic stage. Pause the video here a moment and do that, please. Okay, so this always causes a little bit of confusion in class because there's 1 or 2 annotations that technically could go either way round, really. So here's the correct order. The lava flow is channeled into one stream by the shape of the land, by the relief, and it will start to sort of burn down over the original channel, and sometimes it might flood over the edges and cools to start to begin to form stacked layers of lava like they are. See, this height is different here. Stacked layers of lava. The top layers of the flow cool and solidify to begin to form the ceiling, and over time the lava also melts downwards even further, deepening the channel. Finally, the volcanic eruption stops, the flow finishes, leaving an empty tube. Now I can see where a couple of these you might have put them other way round. Just pop on a couple of arrows to correct any mistakes you've made. Okay, moving on to the next feature, we're going to look at geysers. Now, geysers, you might hear it called either one. It's a little bit like a water volcano, but at the same time not. So what's happening here is in areas of the world where you've got geothermal energy, heat from within the earth, so the magma inside is quite close to the surface of the crust. The heat from that magma causes any underground water to become superheated. And as that water is heated, it expands and creates pressure and creates a process called fleisching, which is really quick transfer of water to steam and to gas and to vapor. And that really quick fleisching creates pressure and expansion, and then the water forces its way up and out of the cracks underneath the ground, creating an eruption of water, essentially. Anyone that's been to Iceland, we went to the geyser fields. There's a really famous one in Yellowstone National Park as well, known as Old Faithful. It's called Old Faithful because it pretty much erupts almost predictably every 45 to 125 minutes. And it ejects water anywhere up to about 50 meters high into the air. And the reason it happens on a cycle like that is once the eruption happens and the pressure is released, all of the cracks in the chamber underground is now empty of water. So water will drain in from the surrounding bedrock, and as it drains into the cracks in the chamber underground, it will get heated by the geothermal energy, and it will expand and it will erupt. and then the space will begin to fill up again. So it's a cycle of building and releasing pressure of water. I'm going to show you some animations to help you understand what's going on with these. So first of all, now this guy talks pretty fast, all right? So see how much you can, oh, okay, doesn't like it. But if I press escape, it'll cancel the recording, so I don't really
It's kind of a big deal. Hey guys, Trace here for D-News, and geysers are fascinating to me, if for no other reason that until today I did not realize that I knew nothing about them. I mean, I assumed I knew some things, but I didn't know. You know what I mean? Maybe you're in the same boat. Let's see. I understand volcanoes. It's, a magma bulb underneath a mountain, and the magma builds up and slowly builds pressure until boom, an explosion, and you got a volcano. I understand earthquakes. It's two tectonic plates, and they butt together, or they move around, S waves, P waves, it's earthquakes. The term geyser comes from the Icelandic word to gush, which is a carryover from a discovery of one in 1294, which is the oldest on our planet. Geysers aren't just water volcanoes. They're more like nature's tea kettles. It requires a precise mix of conditions to make them work, which explains why they appear in groups called fields. Over half of the world's geysers are in Yellowstone National Park, including the largest, as in the most powerful, which is not Old Faithful, by the way. It's the Steamboat Geyser. This fella can spew hot vapors and steam 400 feet into the air, but as a catch, it only does so sporadically. Last Wednesday, it erupted for the first time in 8 years. The spewing just went on and on. It was 300 feet high, and it went for 24 hours straight. So why do geysers not just go off all the time? Because they're a natural balancing act. Geysers occur when conditions are just right. Mainly in Iceland, Chile, New Zealand, and the United States, by the way. A geyser needs a heat source. Geothermal energy comes from within the earth, and the reason geysers come in groups is because they're sitting on top of a high concentration of that energy. When water pools underground or collects in layers of porous stone near the surface, the magma, sitting about 3 miles below that, superheats it, keeping that water high above its boiling point due to the pressures involved under the surface of the earth. The balancing act comes in because of the heat and pressure. As the water heats near the magma, a small amount will squirt from the surface, releasing that pressure. But if the heat builds up too much, the boiling overwhelms the pressure of the rock, and then an eruption of steam happens. Woo! The steam quickly expands to 1,500 times the original volume of the water, and the eruption will continue until the geyser is dried out, or until the heat and the pressure of the earth goes back into a balance, and then we get that trickling water again. It is crazy cool, to put it just right. Now that we know how geysers work, that other more famous Yellowstone geyser makes more sense. Old Faithful gets its name because that particular one erupts about every 45 to 110 minutes. It must have a constant level of heat and pressure under there, so it keeps itself fairly balanced. If you were going to visit, you'd probably see that one, but not the Steamboat Geyser go off because it took 50 years to erupt once. It may not go off again for a while. Have you seen a geyser erupt? If so, where were you? Tell us all about it. And thanks a lot for watching D-News today. Make sure you subscribe to keep getting our videos every day. I'm Trace. See you later.
Okay, I just need to try and now figure out how to get out of this without... No. Ooh. Techie. Okay, because if I press, like I said, if I press escape, it'll end the screen recording, and I don't want to do that. Right, you're going to create your own diagram of how a geyser works. Now, that last explanation might have been a little bit quick, so this one might help you a little bit more.
A geyser needs at least 3 things to work. The first is a water supply, usually cool, shallow groundwater or surface recharge, to refill the geyser after an eruption. The second is a heat source. This is not lava or molten rock, but normally superheated water, forced up through cracks under high pressure. Finally, a geyser needs a plumbing system to store the water as it's heated. This is often a vertical shaft or conduit, perhaps connected to other voids or spaces nearby. This plumbing system needs to be pressure tight. In a geyser, this is due to a layer of mineral, called sinter, that is deposited on the walls of the conduit. Over time, more and more of this sinter may be deposited, sealing the walls and perhaps narrowing channels. At the surface, the sinter builds a platform or cone of gray geyserite over hundreds or thousands of years. An eruption cycle starts with the conduit being filled by the superheated water from below, perhaps from multiple points. This water is much hotter than the normal boiling point, so a portion of it flashes immediately to steam as it squirts out of the fissures. Cooler, shallow groundwater also starts filling the chamber from above, mixing with the hot fluid from below and raising the water level over time. Filling the plumbing system can take anywhere from seconds to days. As the water rises, the pressure at the bottom increases due to the weight of the liquid above. Boiling is suppressed by both the cool, shallow water and this increased pressure. But the hot fluid below is still heating things, and the water temperature starts to climb. Superheated steam from below rises and condenses in the cooler waters above, warming them until the entire conduit is close to its boiling point at that depth. Now if a boil or rising bubble spills off some water from the top, the pressure will be reduced and the water throughout the conduit will start flashing to steam. Bubbles will grow larger as they rise, and the pressure of the expanding steam in the system throws the water out of the geyser and into the air, forming an eruption. With no extra pressure, much of the remaining water is ejected as steam, and the empty geyser can start refilling for the next cycle.
Okay, so if we go back to what we were discussing with the PowerPoint. Alright, so I've taken a screenshot from that video. You've got your three things here. Here is your underground chamber, holes in the ground, basically. Thing number one that you need. Thing number two, cold groundwater from cracks in the bedrock, and superheated groundwater, the third thing that you need. So somewhere down here, fairly close to the surface, there is a lot of geothermal heat from magma, and it has superheated some of the deeper groundwater here. So the superheated groundwater drains into the chamber, it mixes with the cold groundwater, and that causes all kinds of physical reactions that change the pressure and cause the water to reach its boiling point, flash to steam, and cause an eruption of water out the top of the geyser. This geyserite that he was talking about, what it does is it's sort of like a natural concrete. So this water is really rich in minerals, and over time those minerals get deposited and they build up on the outside of the chamber, and it creates like a natural concrete that sort of seals off the chamber to allow really high pressure levels to build up. So part one, the geyser fills with cool water from the surrounding groundwater stores. The cool water is added to by superheated water that's been heated by the magma at a greater depth, and those things will mix and it creates pressure and expansion, some of it turning to steam, and eventually the pressure becomes so great that it will erupt at the top of the geyser crater. So I would like you to take as much space in your book as you want, make your own version of this diagram as best you can, take your time, don't let it phase you, and then just put these three annotations onto your diagram around it, please. So pause the video here a moment and go ahead and do that. Okay, and that brings us to the end of lesson 4. So we've got large-scale volcanic features, your stratovolcanoes, your shield volcanoes, your geysers, and your calderas. And then you've got your small-scale volcanic features, things more like your cinder cones, your lava tubes. Okay, so when we're talking about volcanic landscapes, we're not just, they've categorized geysers as small-scale actually, not large-scale. So when we're talking about volcanic landscapes, we're not just talking about volcanoes, we're talking about their associated features as well, the lava tubes, the geysers, and the calderas. So, well done, lesson 4 done. I'll see you soon for lesson 5. If you need anything at all, drop me an email, gleasona@hopecamry.net.